Hello everyone and welcome back to another science reviewer. Today we're going to be talking about speed, velocity, acceleration, and UAM. All right, so let's get started. It's actually pretty tricky for me to narrow it down, so I'll just box when I'm done. When I consider it done, like 70% done. All right, let's start. So what's the difference between speed and velocity? So speed is how fast an object moves, so regardless of its direction. This is calculated by using the distance and time, and is also scalar, which means you don't need a direction for it. It uses the total distance over time to find the speed, or v average. So an example of which is like let's say your distance is 100 km, and then it took you, let's say, 2 hours. So therefore you have 100 divided by 2, that's 50, and then that's kmh. So that's an example of a speed. So how about velocity? So velocity is the rate of change from an object's origin, and we'll see this later. This uses displacement and time to calculate it, and is a vector quantity. It also uses the formula resultant displacement over time is equal to velocity. So that's the difference between speed versus velocity. By the way, just a reminder, when an object goes north or east, that's a positive for vector quantities. But if it's going south or west, that's a negative. Let's apply that in our sample exercise 1. Sample exercise 1 tells us that a car travels from point A to B with a distance of 200.0 meters in 40.0 seconds. If it then traveled back and stopped at point C within 25.0 seconds. Okay, what's the average speed? So we're given this diagram over here, and let's solve for the distance first. So let's do A first. So to find the total speed, we need two things, the d sub t and the time. So time is given. We have 40 seconds and 25.0 seconds. So right here and right here. So all you need to do is to put 40.0 plus seconds plus 25.0 seconds is equal to 65.0 seconds. Remember, follow the significant figures. Next, we're going to need to find the d sub t, or the total distance. So from the diagram here, we can see we have 0 to 200. So we have 200.0 meters. Plus, we also have 200 to 100. 200 minus 100 is 100. So 100.0 meters. That's equal to 300.0 meters. So there we go. Now that we have the values, I'll just go get my calculator, and then we can start solving. So let's recall our formula. That's d sub t over, that's d sub t over time. That's equal in this case to 300.0 meters over 65.0 seconds. So we put the raw values into the calculator. We have 300.0 divided by 65.0. That's equal to 4.61538, so on and so forth. Recalling significant figures, we have 4 significant figures over here and 3 significant figures over here. Remember, this is 4 significant figures because of the decimal point over here. So all of these zeros are significant. Same thing here. This zero is significant because we have a decimal point over there. So we have 4 significant figures above and 3 significants on the top. That means we need to follow 3 SFs because it's the lowest amount of SFs. So that's equal to 4.62 because this is this is a 5, so we round up this digit over here. So we add, and then we add meters per second. So that's our speed. Time for velocity now. So for velocity, we have, once again, we need d sub r and time. So time, you can just copy and paste it because there's nothing that changed anyway in the given scenario. So you're still left with 65.0 seconds. But for this what do you call this? Resultant displacement. There you go. Sorry, resultant displacement. We need to find the direction of the car going in relative to what will we put as positive and negative. So we went from 0 to 200 meters in this direction, and as you can see by that diagram, we're going this direction to the right is called east. So east is, as you can see over here, positive. So we put 200.0 m meters, and then what's next? We have 200 to 100, but that's going west, which west over here is negative. So it's gonna be minus 100.0 meters because it's west. It's going westward. That's equal to 100.0 meters. All right. Now we can calculate once again. D sub r is equal to, over t is equal to 100.0 meters over 65.0 seconds. Let's put that in the calculator. That's equal to 1.5384 dot dot dot. But following 3 SFs, because it's almost the same case over here, we get an equal value of 1.54 rounded off meters per second. So that's your velocity, and this is your speed on the left. Okay, that's the simple bit. Yeah, it's already a bit overwhelming, but that's the simple bit. What if, let's just say, the displacement isn't in the straight line and it forms a triangle, believe it or not. So this is going to be our next sample exercise. Sample exercise 2. Skater boy Brando scooted to the nearest to the east by 135.0 meters, and he decided to go north and stop at 250.0 meters. He finished his journey within 240 seconds. So let's analyze it and try to make a diagram. Skater boy Brando started here, let's just say that, and then he moved 135 meters east. Something like this. Let's label this. And then he went 250 meters north. Now this is our diagram. But you see these 2 points over here, right? They can be connected through one line. You don't have to go through this line because remember, displacement is just from point A to B, start to finish. So we can just draw this dotted line over here. So this is going to be our displacement. So in this case, we have a right angled triangle. And then we want to find the what do you call this? Yeah, this red line. So to find it, we want to do a squared plus b squared is equal to c squared. So that's how we do it. It's the Pythagorean theorem. Let's put it. So 135.0 squared plus 250.0 squared is equal to c squared. So let's do that. So 135.0 squared, that is 18,225 plus 250 squared, that's equal to 62,500, is equal to c squared. Add both these values up. 80,725 is equal to c squared. And then square root your answer in the calculator to get okay, we follow the same significant figures, so 284.1 meters equals c. So that is your displacement, 284.1 meters. Now we can start solving. But yeah, now we can start solving. So let me just get ready. Okay, I've got it. So first and foremost, we need to calculate the speed. So speed. That's going to be d sub t over t. So d sub t is equal to our two lines over here, the ones in the given that we didn't derive. So that's 135 meters plus 250.0 meters equals 385 meters. We are also given that t is equal to 240 seconds. So let's use the formula. D sub t is equal to d sub t over t equals 385.0 meters over 240 seconds. Put that into the calculator and you get 1.6 meters per second. And we only use 1.6 meters per second because this has 2 SFs while this one has 4. So we need to use 2 SFs, least SF. Next, velocity. Now that we have d sub r, let me just make that clear. Let me just make this clear. This is your d sub r. So that's your d sub r. And to find that is already given. We have used the Pythagorean theorem. So you do 284.1 meters. And same time is 240 seconds. And then we have 284.1 meters all over 240 seconds is equal to, let's put that in our calculator, 1.18375. But once again, we need 2 SFs, so it's 1.2 meters per second. So we have two types of velocity problems, the straight line and the triangle. So there's obviously going to be like other problems, but those are going to be, that's actually a college and senior high level. So for grade 10, this is what we have to deal with right now. So yeah, take a screenshot if you wish, and we're gonna move on to velocity right after. Alright, so acceleration is the rate of change of velocity. So whenever this velocity changes, it's considered acceleration. So this happens when either it's a vector quantity, by the way. So we use the use the north, south, east, and west. And then it happens when there's a change of speed or a change of direction. Now the formula for this is actually acceleration is equal to v sub f. So velocity final minus velocity initial all over delta time, which is just your time. But as you can see over here, unlike these formulas which only have 2 variables, this one has 4. So that means deriving is required as you only want 1 unknown. So as you can see, A is clearly derived here, but what if we're missing v sub f, v sub I, and t? So let's derive together. So v sub f minus, now let's first start with this one, v sub f minus v sub I over delta t is equal to a. First thing we're gonna do is we're gonna cancel the t. So it becomes v sub f minus v sub I. And since we multiplied both sides by t, we cancel this one, but we also have to add a t over here. And finally, now we just have to transpose. So v sub f is equal to at plus v sub I. So it becomes plus because we change it to the other side. And that's our first formula. The second formula, let's derive it from here. We have v sub f again minus v sub I all over t, delta t is equal to a. Then once again, we multiply both sides by t. V sub f minus v sub I is equal to at. Next, we then transpose the v sub f, right? You have v sub f, so it becomes negative vi is equal to at plus at minus v sub f. And then since this is negative, we just flip the signs all over. So it becomes v sub I is equal to negative at plus v sub f, or v sub f minus at. So either one of these works. I'll highlight them for you. Lastly, we're gonna do t. So there's actually an easier way to do t, and I'll show you right now. So v sub f minus v sub I over t is equal, delta t is equal to a. Then we want to cancel t again. V sub f minus v sub I is equal to at. Then this time we cancel a. We want to divide by a. So v sub f minus v sub I all over a is equal to t. So we just kind of flip the position, but that's a step-by-step process. So there we have it. We have all of the possible formulas related to acceleration. So we're gonna solve problems later. For now, this is where I'm just gonna take a short, maybe a little break, because I'm still a bit tired from yesterday. Okay, so we're going to now be doing a bit of problem solving, speeding up and slowing down. No applications yet. We're just gonna use this table to find the missing values. We're gonna apply everything, by the way. So first and foremost, we're missing acceleration. So therefore, we have to use a, the one with a on the side. So we need to give input the given. So I'll just go by row. This is number 1. This is number 1, this is number 2, this is number 3, and this is number 4. So for number 1, we use the formula A equals v sub f minus v sub I over t. So in number 1, we're given 2.0 for t, and then we got initial velocity is 10. Final velocity first. Final velocity is 14.0, and then we got final velocity of initial velocity is 10.0. That's equal to 4.0 over 2.0, which is equal to 2.0 meters per second. Okay, 2.0, so we just put plus 2.0. Next one, we're missing final velocity. So final velocity, we use this one. Final velocity equals at plus vi. So we use v sub f. This is number 2. V sub f is equal to at plus vi. So we have acceleration is 2. And then time is also 2. And then we have plus v sub I. Ooh, that's a minus 10. So we have 4 minus 10, and that's equal to v sub f is equal to negative 6.0. Sorry, there you go. Negative 6.0. What's this? Meters per second. So it's negative 6.0. Next is number 3. Number 3, we have initial velocity missing. So we're gonna use the second one. V sub I is equal to V sub f minus 80. So V sub I is equal to V sub f minus 80. So so we have V sub f final is 6 minus, what's the time? 2. And what's the acceleration is also negative 2. So that becomes 6 minus negative 4, which is actually just 6 plus 4. So that's 10. 10. So 10 meters per second. And then lastly, we have the time interval. So let me just make a little box here so it's not too confusing. Number 4. We got, sorry, time interval missing, so we have to use this one with t. So v sub f minus v sub I all over a is equal to t. That's equal to v sub final is negative 14, and then minus negative 10 all over acceleration, which is negative 2.0. That's equal to so that's negative 14 plus 10, so that's negative 4.0 over negative 2.0 is equal to 2.0 meters per second. So let me just check the answer key to see if this is correct. Okay, let's just check. So this is correct, and correct. Okay, yeah, this is all correct, but let's see if it's speeding up and slowing down. So it speeds up when the initial velocity, when the final velocity is bigger than the initial velocity. So this is, by the way, this is just taking the raw numbers, so you don't have to check the minus. So just ask yourself, is 14 bigger than 10? If yes, it's speeding up. Now, is 6 bigger than 10? No. So therefore it's slowing down. So, next one. Is 6 bigger than 10? Still no. So slowing down. And lastly, is 14 bigger than 10? No. Yes, it is speeding up. So what have we come to realize here? Take a look at the time, and what can we look at? So we want to try to find the pattern over here. Okay, I think I get it now. Alright, so as you could see over here, the acceleration is positive, and the initial and final velocity is also positive. So that means it's speeding up in the positive direction. But as you could see in these middle two over here, the acceleration is positive, but the velocities are negative. That means they're slowing down. Same thing here. Negative here and positive over here. So if the acceleration and velocities are opposite, that means it's slowing down. But if it's speeding up, that means it's either going in the negative direction or the positive direction. So I'll show you the table after this. But for now, I'll definitely take a break. I'm still pretty tired, so that's why I'm taking this one step at a time. I can't really speedrun this. But yeah, hopefully it's helpful so far. Alright, so now that we have the basics done, let's try to apply it. So let's start with this one. Bruno Mars is almost late to his concert in Bulacan, so he asks his driver to speed up the car. The driver then presses the gas pedal, and the car moves from 18 meters per second to 25 meters per second in 1.40 seconds. What is the acceleration in meters per second squared of the car, assuming uniform acceleration? So since we have 4 variables, it's best that we have 3 givens. First and foremost, and the car moves from 18 meters per second. So the from in that phrase indicates that our v sub initial, because that's the starting, is 18 meters per second. Next, to 25 meters per second. So to 25 meters per second indicates that that's the final velocity. So that's the 25 meters per second. In 1.40 seconds, that indicates time. So time is equal to 1.40 seconds. Now, we're missing for the acceleration. So let's use this formula because it has a at the other side. So a equals v sub f minus v sub I over time, right? And then we have a equals 25 meters per second minus 18 meters per second all over 1.40 seconds. So if we put that into the calculator, that's equal to a sub equals, so we minus these two, that's equal to 7.0 meters per second all over 1.40 seconds. So your acceleration is equal to 5.0 meters per second squared. Alright, nice one. But what about, there's problems that seemingly if you read the entire thing, there's only 2 given, like this one. Pole vaulters like E.J. Obiena make a preparatory run before every pole jump attempt. If E.J. accelerates at 1.8 meters per second in 5.50 seconds during his preparatory run, what is his final velocity? So it's clear that we don't know the VF, because it's clearly, yes, we don't know the VF. But we do know the acceleration rate, that's going to be 1.8 meters per second squared, and we have the time, that's gonna be 5.50 seconds. But wait, we weren't given the v sub I. But let's read again. Pole vaulters make a preparatory run. Now, when you're running, think about it. Are you already at speed, like at rest? Are you already moving? No. Since you're not moving, our v sub I is actually 0 meters per second. So in some cases, you do need to use a bit of critical thinking. So now that we know that all our variables are identified, we need to use which has v sub f. So v sub f is equal to at plus vi. So let's write that down. V sub f is equal to at plus vi. So we have v sub f is equal to, acceleration is 1.8 meters per second, and then we get time is 5.050 seconds plus our v sub I, which is 0 meters per second. That's equal to v sub f equals, so 1.8 times 5.5 is 9.9 meters per second. So it's gonna be like this in our next topic, which is UAM. It's actually the last topic. So yeah, because of how weirdly all over the place that's why we haven't knocked anything down. So yeah, it's gonna be one clean swoop. But I'll be real with you though, this is probably one of the most space efficient ones I've made. I'm kind of proud of this one, even though it took me like an hour. Yeah. All right. I'll see you. I'll take a short, probably like I'll probably have to go to a meeting soon. It's almost 2 p.m. I'll take a rest and join the meeting. I'll probably start recording again in 3. So see you then. All right. Next one is going to be graphic analysis of motion. It just gives a visual representation of motion, and it helps you actually visualize stuff and find patterns within, the previous topics. So here are some examples, but I'm gonna do the types now. So the types of motion. Number 1, this one is called at rest. Here on the left, we see a displacement on the vertical axis and time at the horizontal axis. And as you can see, as time moves on, it seems like there's no displacement change. And that's right, because once again, it's at rest. It's never gonna change because it's at rest. It won't move. So hence, the displacement never moves up or down. No, it just stays here because once again, it's at rest. For the velocity, once again, since velocity is the rate of change in like speed, sorry, no, that's acceleration, but like since velocity is the change from the object's origin, and as you could see, it's still staying the same at exactly at 0, it's because there's no velocity. Once again, the object does not move, hence why the velocity is 0. Next one, moving in positive direction with constant velocity. So this time for our displacement or position, as you could see, as time moves on horizontally, we also get a vertical change. I have written 2 lines here. One of these objects is faster, the red one, because as you could see, by this point in time, the red is higher than the blue. So this means the red object is moving faster than the blue object. As you could see, it's a completely straight line. This means it's moving at a certain rate, hence why the slope is constant. For the velocity, on the other hand, it still remains constant because there's no change in the speed, because it's a constant velocity. Therefore, even though we are moving, it still moves at the same speed, hence why the red line is higher, because higher up the positive scale because it's faster, and the blue line is lower because it's a slower one, but it's still moving. Both are still moving. As long as the velocity is not 0, it's moving in some way. Same logic can be applied here for number 3, moving in a negative direction with constant velocity. So this time, instead of the it's the mic still on? Okay, good. Okay, sorry about that, but moving in a negative direction with constant velocity. So as we could see, the starting position is initially high, but once again, you just need to look out for the lines here. So as you can see, let's say we start off 100 meters from position and we're moving in a negative direction. So that 100-meter displacement is going down as we speak. As you can see over here, the red line is representing a much more drastic drop. And meanwhile, the blue line is representing a more steady decline. Both of them are going back to their origin, or the origin of the displacement, hence why they're approaching 0, which is this one. So therefore, in velocity, the blue would actually be above the red. Why? Because blue is like, let's say, negative 2 meters per second. And then red is negative 4 meters per second. So, as you can see, negative 4, negative 6, it goes down to negative infinity. So that's why we put the blue line above the red line. As you can see over here, just copy the position. So if blue line over here is over the red line, copy it here, blue line over red line. It's that simple. Now we move on to acceleration. Now our velocity is not constant anymore. First one, moving in a positive direction with acceleration. So that means we're speeding up. So as you can see over here, we have a curve now. But why is that the case? As you can see, as time moves on, we start off slow, but eventually we get faster and faster and faster and faster and faster. So something like that. Why? Because our velocity or rate of change in speed is also changing. It's going upward. So hence, as our velocity moves upward, we can expect an even steeper slope over here. The higher this line goes over here, the steeper of a slope you can expect over here. Because, once again, we're just speeding up and hence the displacement moves so much faster than time itself does. Same thing here with the moving in negative direction with acceleration. So as you could see, we're starting from, let's say, 1 kilometer away, 10 kilometers away. And then we start to slowly go back and rapidly go back over here. And that's also the reason why we are still speeding up. As you could see, our velocity starts at 0, but does -1, -2, -3, -4, -5, -6, and so on. And that's why you can observe the graph starting to drastically drop over here. It's because our velocity is going much faster on the negative axis. So that's why we have that. Next, moving in a positive direction with deceleration. So negative, starting to slow down. We're slowing down. So once again over here, we start off fast, but as we continue as time goes on, it looks like we're about to hit a flat line, and eventually we'll hit that. And then yeah, same thing here for the velocity. As you can see, we just expand all the way here and we approach 0, and hence why it goes to a rest. So if you expand these lines, as you could see, this will mean rest, and this will also mean 0 velocity, which means also rest. So therefore, since we're using the dt, right, graph here, that's why it starts to slow down as we approach 0 velocity. And last one, 7, moving in negative direction with deceleration. So the displacement, as you could see, starts off high, but it goes eventually to 0 because we're moving on a negative direction and we're approaching 0 displacement. Same thing here. Since we're slowing down, we start off at negative, let's say 5, but then it becomes -4, 3, 2, -1, and then hits 0. And hence why the rate is here. So we eventually hit 0 on both sides for this scenario. So what have we noticed here, and what have we seen? Well, for UAM, as you could see, we see that the velocity is not fixed, and the dt graphs show a curve. But for the non-UAM here, we see the dt graphs, they're not curved, they're straight lines, and the velocities are constant. So but just by looking at these graphs, you can immediately categorize which belong to UAM and which do not belong to UAM. Alright, so here are our UAM equations, and it's pretty complex, so I'll just explain along the way. But here, as you can see, we have the uses and the missing variables that you cannot use. So if you're missing this variable here, you cannot use this formula. If you're missing, I believe, like 2 or 3 you need 3 givens. So in order to use any of these formulas. So let's start. Number 1, you're driving at a steady speed of 17 meters per second, and when you see the orange traffic light, instantaneously, and being the responsible driver that you are, you begin to apply the brakes, which means your car constantly decelerate. If you halt to a stop after 4.0 seconds, A, what's the distance in meters you covered before it's stopping? And B, what's your car's deceleration in meters per second? So as you could see, we have a total of 5 variables we're playing with here. So first and foremost, a steady speed of 17 meters per second indicates that this is your V sub I, as this is the start of the problem. So let's write that down. Next, we are also given that we halt to a stop. Stop meaning 0. So V sub F is equal to 0.0 meters per second. Next, you know that you come to a stop after 4 seconds, which means that's your T. 4.00 seconds to be more precise, actually. Next, you need to find the distance, which is unknown, as well as your acceleration, which is also unknown. Let's start off with letter A. So for letter A, we need to find a formula that solves for that has 3 of these and solve for distance. So first and foremost, let's eliminate. So we have v sub I, v sub f, but there's no distance over here. So equation 1 is out of the window. Next is equation 2. These we do have distance over here. We are given v sub f, we are given v sub I, and we also have delta t, which means this is the correct one to use. So in this case, we're going to use this one. So formula to use is gonna be number 2. So let me just make my pen a bit thinner. So that's displacement is equal to v sub f plus v sub I over 2 in parentheses delta t. Let's substitute. V sub t is equal to v sub f, which is 0.0 meters, 0.0 meters per second, plus 17.0 meters per second, all over 2 times delta t, which is 4.0 seconds. That's equal to the 17.0 that's a constant, right? 17.0 meters per second all over 2 times 4.00 seconds. So when we put this into the calculator, 17.0 divided by 2 is 8.5. So 8.5, right? 8.5 meters per second times 4.00 seconds, which is 8.5 times 4 is equal to displacement is equal to 34 meters. Yeah, correct. So that's our answer over there. Distance is 34 meters. Alright, that's good. Now let's do letter B. What's your car's deceleration in meters per second? So first and foremost, we want to find for A, so it's missing here, so we don't use equation 2. We have v sub I, v sub f, and t, so we can use this one. So equation 1 it is, but we do have to derive it. So let's start. Use equation what's this? Equation 1 as equal to and derive. We have v sub f equals v sub I plus a times t. V sub f is equal to, oh, I forgot the arrows, did I? Yeah, hold on. There you go. V sub f plus is equal to v sub I plus, isn't it a delta t? Yeah, a delta t, or just at. So we want to derive a. So v sub f minus v sub I is equal to a delta t. We want only a, so v sub f, we divide both sides by t. We get v sub f, v sub I, all over t is equal to acceleration. Then we substitute. We got v sub f, which is final 0.0 meters per second, minus 17.0 meters per second all over time, which is 4.00 seconds. And then we get negative 17.0 meters per second all over 4.00 seconds. And then we put that into the calculator to get negative 17.0 divided by 4.00. That's equal to negative 4.25 meters per second squared. And yeah, that's correct because we need to follow 3 SFs. So that's actually a nice one. Okay, I need to adjust this. No, I'll just cut it off. Okay, there, that'll do. Alright, last problem. A bullet penetrates a lump of clay ballistic tester until it stops at a distance of 0.070 meters at after 0.085 seconds. So, now this one's a bit different because for real now, we are actually only given two. I think we have to solve A first before B. So let's do this. So we need to find the velocity first. So seeing as it's just a straight line, the shot is a straight line, it doesn't matter. So we can just do this number divided by this number. So let's write our given. 0B given 0.070 meters and 0.000 585 seconds. So we need to divide this. So in the calculator, oh sorry, this is A. So 0.070 m over 0.000585 s is equal to, let's put that, 0.070 divided by 0.000585 is equal to, we have two SFs here, and how many is this? 3 SFs here. So we need 2 SFs. 119.65 and then equals 120 because we want SFs, meters per second. So that's our letter A. Letter B. What is the acceleration of the bullet in meters per second squared while moving the clay? So for acceleration, all right, hold on, I'll review this one. All right, so this is gonna be our v sub f, because that's our velocity, final velocity. But our v sub I is obviously 0, because once you're just holding a gun before, or a bullet, a gun, if you're just holding that and it's at rest, it's obviously 0. So we put this into our calculation. So A is equal to V sub F, which is our 120 meters per second, minus our V sub I, but we can cancel that, so it's just because it's 0, so that's equal to T. T is 0.000585 seconds. So 120 divided by 0.000585 is equal to alright, this is equal to 205,128 meters per second squared, which is actually not surprising at all, because this is a bullet. This is a bullet and it's expected to have this large of a quantity. Like you won't see a bullet just going slowly. So we need we have 3 SFs over here. We have, oh no, this is 2 SFs. Yeah, this is 2 SFs. So 2 SFs means we need to round up this one, which means 210,000 meters per second squared. So that's your acceleration, and that's your letter B answer. And just like that, it was quite a mess to solve for everything because everything was over the place. But we have completed everything, which means yes, I'm probably gonna upload this in like an hour or two. So yeah, thank you guys so much for watching, as well as to the science head in my school. Thank you so much for sending it all the way to the other campus we have as well. We've hit nearly 500 views on that video. That was the highest amount of views. So really, thank you guys. Thank you to the science head for their support as well. And I'll see you guys in the next one. Take care of yourselves as we're approaching the end term assessments. We'll make a review for that one. Don't worry. See you then.